Page 4 of Vector Apps Addendum. Number 4, find the equation of the plane containing the following points in vector form and in Cartesian form. Well, in order to find Cartesian form, you first need to find vector form anyway. So let's go ahead and do vector form first. So to do vector form, we need a couple different things. One of the things we need is a starting point on the plane. So let's say that would be point A, which we have A, B, and C, but we'll choose point A. And then we also need a normal vector, which defines the orientation or the direction of the entire plane. Okay, so we already have the point. All we need now is a normal vector. To find the normal vector, the easiest way to do that is to find the vector AB and the vector AC. And then what we'll do is we'll take the cross product of the two, and then we'll find a vector which is perpendicular to both AB and AC, and consequently perpendicular to the plane. Okay? So, first let's find AB vector, which is equal to 1, 3, 2, minus 0, minus 2, minus 6. It's equal to 1, 1, negative 4. Right? And let's find AC. AC is equal to negative 1, 2, 4, and we're going to subtract out 0, 0, 2, 6, and we end up with negative 1, 0, negative 2. And now we're going to take the cross product of the two. So 1, 1, negative 4, cross product with negative 1, 0, negative 2, and then the cross product of these two would be negative 2 minus 0 would be negative 2. And the next one would be negative 2 minus 4, which would be negative 6. But we take the negative of that, so it would be positive 6. And last of all, 0 minus negative 1. 0 plus 1 is 1. Okay, so the normal vector is negative 2, 6, 1. And we know that the point that we want to use is point A. So now we can write the equation. Basically what we're going to say now is that, well, we can define all the points x, y, z. We'll say that this is a possible x, y, z point. Okay, we can define all the points x, y, z by saying, okay, the vector x, y, z minus the vector a, which is 0, 2, 6, is perpendicular to the normal vector. And when we say it's perpendicular to the normal vector, we will do a scalar product with the normal vector, and we will set that equal to 0. Okay? So basically what that does is it defines like all the points x, y, z which satisfy that condition. Okay? Then how do we change that? And so this is the answer to 1. How do we answer 2, which is the Cartesian form? All we need to do is do the scalar product and expand it. So that would be x times negative 2, 6 times y minus 2, and 1 times z minus 6. And that is equal to 0. Okay, so now let's just combine like terms. And so that's the variable terms look like that. And then on the constant terms, we have minus 12 and minus 6. And then we'll take minus 12 minus 6, which is minus 18, and we put it on the other side because that's kind of the standard form for Cartesian plane equations. And so what's kind of cool here, you'll see is the coefficients of the left side, negative 2, 6, 1, are the same as the normal vector. Okay? And so that's it for number 4A. Okay, now they want the equation of a line which goes through this point and is normal to this plane. Okay, so remember what we just said about the previous problem. When you look at the equation to a plane, you can actually pick out the equation of a line, equation of the normal line, by looking at the coefficients. So actually the coefficients here, which are 1, -3, and 4, are the normal line coefficients. 1, -3, and 4, that's the vector of the normal line for that plane. So we already have the direction of the line that goes through the plane, 1, -3, 4. Now what we need to do is make that line go through this reference point. And so remember that the way the equation of a line looks is xyz equals, and then a position vector plus lambda times the direction vector. And if the direction vector is the normal vector, then we got that done. And then if we want to go through a point 1, -2, 0, we could just make that into the position vector, and then we're completely done. Pretty easy, right? Okay. That just kind of looked hard, but once you start doing it, you're like, I have all the information already. It's like a write down problem where they tell you write down whatever because you can already see that the answer is here. Find the parametric equations of the line through these 2 points. Okay, and we'll do that first without even reading B. Okay, so to make the equation of a line, let's just write the vector equation of a line first because that's something that I think you do on a more regular basis. So basically what we need is we need a position vector. And let's just pick this first one here as the position vector, and then we need the direction vector. Well, how do you figure out the direction vector of a line which contains 2 different points that they gave you? Well, you could just figure out the direction vector by subtracting one of the points from the other and finding the vector between the two. So if we find either the vector PQ or the vector QP, that would be a direction vector that we could use. So let's find the direction vector PQ. So PQ would be equal to Q, which is 2, 0, -1, and we're going to subtract 1, -2, 4, and that will give us 1, 2, and -5. Okay, so now I'm going to write the equation of the line which goes through PQ. So that would be xyz, or you could do r, vector r, if that's more compact. We're going to put the position vector 1, -2, 4. You could put either that one or 2, 0, -1. It doesn't matter. And then I'm going to put plus lambda and the direction vector we just found, which is 1, 2, -5. And next thing I'm going to do is I'm going to write it as a set of parametric equations. And the way I do that is I simply divide it up into layers like this. So the first one is just going to be x equals 1 plus lambda times 1, which is just lambda. We have y equals -2 plus lambda 2. And then we got z equals 4 plus negative, I'm just going to put -5, 4 minus 5 lambda. Okay? And so those would be the parametric equations that they asked for in part A. And then part B, it says, find where this line meets the YOZ plane. Let's recall what the YOZ plane looks like if we have x here, y here, and z here. The YOZ plane is along the y and the z axis. So you can see from this drawing, hopefully, that the coordinate that is always going to be 0 in the YOZ plane is the x coordinate, right? The x coordinate comes, the x axis comes out. The YOZ plane is along the x equals 0 dimension. So if x is 0, that means that if you look at our vector equation, we could say, okay, what would be the coordinates of y and z if we know that the x coordinate is 0? Okay, so let's solve for that and see. Let's see. 1, 2, -5. So you can see that, like, if you know that the first coordinate is 0, then you could kind of solve the top layer parametric equation. It would be 0 equals 1 plus lambda. You can see that this is like if x equals 0, that's what you would get. And you can immediately see that lambda equals -1, right? So we know that lambda equals -1. that means that we could figure out the y and the z coordinates by putting lambda equals -1 here and lambda equals -1 here. We would get y equals -2 plus -2. And for z, we would get 4 minus 5 times -1, which would be 4 plus 5. So z would be 9, and y would be -4. So the coordinates of the point where this line would meet the y-z plane would be 0, because the x coordinate would be 0. The y coordinate would be -4, and the z coordinate would be 9. Let's do number 2 here. It says, when does this line meet the plane with the equation y plus z equals 2? Okay, so if y plus z equals 2, that gives us a clue that we're going to use the other two parametric equations. I need a little bit more space, so I cramped everything into the side here. So what we're going to do now is we're going to take the second two parametric equations, which is y equals -2 plus 2 lambda, and z equals 4 minus 5 lambda. And then we're going to also use the equation y plus z equals 2 to see if we can figure out what lambda should be. Okay, so I think we can, because we have three equations here and we have three unknowns, z, y, z, and lambda, so we should be able to figure it out, right? So let's first take this equation here, and we will try to solve for y, maybe. And then we'll use that expression in the top expression here. 2 minus z equals -2 plus 2 lambda. And then, well, let's solve for z. So we'll have z, -z equals -4 plus 2 lambda. And we have z equals 4 minus 2 lambda. And then we could take the second expression we have for z, which is z equals 4 minus 5 lambda, and we can set them equal to each other. So we have 4 minus 5 lambda is equal to 4 minus 2 lambda. So you could see that actually -5 lambda is equal to -2 lambda, and that means that lambda must be 0. So if lambda equals 0, then that means we could use the first equation, y equals -2 plus 2 lambda, but to find out that in this case y is actually equal to -2. We could use the second equation, z equals 4 minus 5 lambda, find out that actually z in this case equals 4. And then we'll go back and take the x equals 1 plus lambda equation to find out that x is actually equal to 1. So in this case, the coordinates we're looking for is 1, -2, 4. Okay, so that is the point where the line would intersect the plane with the equation y plus z equals 2. Okay. Finally, part 3, it says to find the line with the Cartesian. We're going to find the intersection of the line that we wrote the equation for with the line with Cartesian equation x minus 3 divided by 2 equals y plus 2 divided by 3 equals z minus 30 divided by -1. First thing that we'd like to do is we'd like to rewrite this equation into a vector form, because that's the form that I think that we're more comfortable with. Let's do that. So we're going to say that each one of these is equal to lambda, right? And then so first we're just going to take this and lambda here, and we're going to make a parametric equation from that. So we'll find out that x minus 3 is equal to 2 lambda, that x equals 3 plus 2 lambda. And then we'll do that for each one. So for y, we would have -2 plus 3 lambda if we do the same algebra. And then for z, we would have minus lambda and 30 here, I think. Okay, so these are the parametric equations that we derived from that Cartesian equation. And from this, we could build a vector equation by grouping these like that. So basically, the equation in vector form for these Cartesian equations would be position vector 3, -2, 30 plus 2, 3, negative 1, lambda. So that would be the vector equation for that. And now we're going to figure out when this line intersects this line. Remember that line? Okay. So the way we do that is we just set them equal to each other. So let's do that. Don't need to make your car sick here. Copy that. And I'm going to put it here. Okay. And so I can set these equal to each other because we're trying to figure out when they intersect, right? So now we got, one thing I do need to adjust is they can't both be lambda, right? Because, we don't know if these lambdas are the same. So what we're going to do is we're going to make one of them into S, and we'll make the other one into T. And now we're fine. Okay, so 3 plus 2S equals 1 plus T. Another equation would be negative 2 plus 3S equals negative 2 plus 2T. And finally, we have 30 minus S equals 4 minus 5T. All right, and then we're going to make these equations into, we'll put S and T on the left, and we'll put the number on the right to make it kind of into a standard form. So if 2S minus T equals negative 2, we have 3S minus 2T equals 0. And we have negative S minus 5T plus 5T equals negative 26. Okay. So now let's see. Let's try to use maybe the second one looks kind of easy because it's got an equal 0 in it. So let's do 3S equals 2T. And then I'm going to say that T equals 3/2 S. And then I'm going to put that in the first equation. So 2S minus 3/2 S equals negative 2. Let me simplify that. So that would be 1/2 S equals negative 2, which means S equals negative 4. If S equals negative 4, I can immediately find T, because I know that T equals 3/2 S. So T is equal to negative 6. And so now we've solved the equation. And so to find out the point where the two intersect, all we need to do is take the S and T and plug it into one equation or the other. And by the way, if you want to confirm that S equals negative 4 and T equals negative 6 is the solution for all equations, you would put it into each one of these equations to make sure it satisfies all the equations, okay? I'm just going to take the second equation here, x, y, z equals 1, negative 2, 4. I'm going to plug in the t value, which would be minus 6. And then I'm going to solve for x, y, and z. So x would be 1 minus 6 times 1, which would be negative 5. Y would be negative 2 minus 6 times 2, which is negative 14. Z would be 4 minus 6 times negative 5, which would be 4 plus 30, which is 34. So this would be my answer for the point where these two lines intersect. Last problem on the page, number 8. Okay, in each of the following cases, find the foot of the normal from A to the given plane, and hence find the shortest distance from A to the plane. Okay. I'm going to draw you a little picture. So the plane, this plane here, is that. The point, this point here, is there. And so what we're trying to do is we're trying to figure out the perpendicular line, which kind of connects the two, connects the plane to the purple point. And this orange line should be the shortest distance. between the two, which means that it's perpendicular to the plane. And so we're going to write an equation for this orange line. It is going to be the position A and the direction vector AF. You might say we don't have the direction vector AF, but the direction vector AF is proportional to a vector which is normal or perpendicular to the plane, and we know how to find the direction vector of the normal. We just look at the coefficients of the plane equation. So we know that the normal vector to the plane, or a normal vector to the plane, is 2, 1, negative 2, so we could use that to define our line. So we're going to define this line here by saying, okay, position vector 1, 0, 2, and then we're just going to add a direction vector 2, 1, negative 2, and that gives us an equation for the orange line. So now we have the equation for the orange line. Now we just need to figure out what lambda is equal to when it hits the plane. The easiest way to do that is to divide this up into three, parametric equations. Okay, so those are our three equations. And now what you do is you just take these equations and you put them into the red equation. So now we're going to have 1 plus 2 lambda plus lambda minus 2 times 2 minus 2 lambda plus 11 equals 0. Now we just combine like terms, and then we can solve for lambda. Combine like terms. So we have 4 lambda plus 4 lambda. So that's 9 lambda. We have 2. We have minus 4, which is negative 2. And then we have plus 11, which is plus 9. So we have 9 lambda equals negative 9. So we have lambda equals negative 1. So if lambda equals negative 1, that allows us to figure out the coordinates of the foot. We just plug it back into the orange equation. And so that will give us that x, y, z, and I'm going to draw in purple now because we are finding the purple point at this time. X, y, z is equal to 1, 0, 2 plus lambda, which is negative 1, times the direction, which is 2, 1, negative 2. And so we get 1 minus 2 is negative 1. 0 minus 1 is negative 1. And we have 2 plus 2, which is 4. So we're not finding point. We're not finding the purple point. We're finding the orange point. We're finding the foot, right? So the coordinates of the foot are negative 1, 4. Now that we have that, we could find the vector from A to F. So the vector AF is equal to the foot, negative 1, 4, minus A. So minus 1, minus 0, minus 2. So that would give us minus 2, minus 1, 2. And so that's the vector representing the point A to the foot. And then if we wanted to find the distance of that point, which would be the shortest distance between A and the plane, all we need to do is do Pythagorean's theorem, 2 squared plus 1 squared plus 2 squared, which gives us square root of 9, which is equal to 3. So, not so bad.